Good morning, good afternoon, good evening, class. This is Mr. ARocena, and on today's video, I'm going to be talking very briefly about Kepler's laws and planetary motion. Now, Johannes Kepler was a physicist, and he studied planetary motion, specifically around our solar system, and a lot of what he talked about kind of plays into the gravity we were discussing in earlier videos. Okay. Now, by no means I'm not an expert astronomer, so how I'm going to deal with Kepler's law is going to be very, very basic. I'll include a link in the description if you guys want to read more about Kepler's laws. But for now, we'll just talk about the main gist of it and the proof. Again, check the description for a link for a more, I guess, in-depth view, in-depth look into Kepler's laws and how it affects planetary motion. All right. So Kepler had three laws, similar, I guess, in a way to Newton, how he had three laws for classical motion. Kepler had three laws for planetary motion based on his study of the solar system. His first law was that planets orbit their central sun in elliptical paths. So not a circular path like we've shown in, say, like elementary classes or even in Science 9 or Science 10. Planets actually orbit their suns in elliptical paths. This is what we call the law of ellipses. Now, the reason for that actually lies in how gravity works in space. So every orbital path is actually slightly elliptical. Some orbital paths are incredibly elliptical, especially for planets that are really, really far out, or depending on how they got into orbit in the first place, their paths can be quite elliptical. So part of the reason why, is this animated? Yes, it's animated. So part of the reason why the path is elliptical is because the sun, or the star in question, will exert some kind of gravity towards the planet. So if I take the planet here, it'll be pulling this way. So they both kind of exert a pull towards each other. So the sun is actually not stationary. It's actually being dragged along towards this planet. If the planet were over here, they would be exerting gravity on each other again. So here, the sun here is exerting a force of gravity on the planet is exerting a force of gravity on the sun. And then similarly over here, and so on. So basically all throughout this orbit, both bodies, both the sun or the star and the planet, are exerting gravitational forces against each other. So it goes to reason then that this sun is actually slowly being pulled this way, then that 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 way, and that way. So the sun is actually kind of moving in this semicircular pattern because it's being pulled along by this. But the force of gravity is not actually equal in all directions, because if the sun and planet are this far apart, because of the way gravity is calculated, so here's our force of gravity. When they are really, really far apart, like here, the force is actually quite small, so they don't actually move towards each other very much. Whereas over here, the distance they're separated is actually a bit smaller, so the force of gravity is stronger here, so they experience more of a pull here. So that's part of the reason why they travel in an elliptical pattern, because the forces aren't equal throughout the orbit. Okay? And that's Kepler's first observation of planetary paths. In our solar system, it's most observable, I believe, in Pluto and Neptune's orbits. They're very elliptical compared to the rest of the planets. The rest of the planets are actually not that elliptical, but they are still elliptical in some respect. Okay? Now, Kepler's second law is that the line is kind of awkward to say. The line joining the center of the sun and the center of the planet will trace out equal areas in equal intervals of time. This is what we call the law of equal areas. So here's an animation for you guys to observe, is that as long as each of these time intervals, so this interval here, if I trace out an equivalent time interval like there, this area 1, area 2 are equal. Area 1 equals area 2. And this is true for all orbits. all orbits, based on his observation of our own solar system, and then we can apply this to other solar systems in the future. So each of these, each area that is traced out, as long as the time interval of this travel is the same, all of these areas are going to be equivalent to each other. Okay. It does seem kind of odd, I guess, especially for some of these really, really long, thin areas. But when you do the math and actually calculate the area, they're all going to be equivalent. Okay. All right, now Kepler's third law. Kepler's third law is the one that's really of interest to us because this one states the following. It's a little wordy. Basically says that the cube of the mean orbital radius divided by the square of its period of revolution is constant. And this is what we call the law of harmonies. And this is really interesting because it allows us to sort of predict and calculate certain things about a particular solar system. K stands for Kepler's constant. So this K here is Kepler's constant. Now Kepler's constant changes depending on the solar system. Okay, so this is really interesting. So our solar system has its own Kepler's constant. Another solar system would have a different one. And even if you consider the Earth and Moon have its own Kepler's constant, because you could consider the Earth and Moon a solar system with the Earth being the center and the Moon orbiting the Earth. So what this basically effectively tells us is that if I know the radius of, that's my radius of orbit, and I know Kepler's constant, then I can predict the period of revolution. And vice versa. If I know the period of revolution and I know Kepler's constant, I can predict the radius of the path. Or if I don't know Kepler's constants, but I know the radius and period, I can calculate Kepler's constant, and then I can predict other things for other objects in that solar system. Okay. So Kepler's constant, this depends on the solar system in question, and it'll be unique for every solar system you encounter. Okay. Or even or other orbiting systems. So if you take the Earth and the Moon, they would have their own Kepler's constant. And it's actually quite useful because then we can use the Kepler's constant of the Earth, and we can predict things like where would we need to launch a satellite so that has a certain period of revolution, or if a satellite has a certain period of revolution, what is its orbit around the planet Earth, or things like that. All right, so let's go through a quick example of using Kepler's third law, in that we're going to calculate K for the following systems. So the first, we'll do the Earth around the Sun. From our best estimates, the Earth is at 1.5 times 10 to the 11 meters away from the Sun, and has a period of rotation in seconds of as follows. So this is basically 1 year in seconds. Okay. So Kepler's law states the following: r cubed over t squared is equal to the Kepler's constant. Okay, so let's throw that into a calculator. So 1.5 times 10 to the 11. And then we are going to cube it, big number. And then we'll divide it by 3.16 to the 7, and we'll square that. And the Kepler's constant, I wish it'd give it to us in scientific notation, would be 3.4 to the 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18. So 3.4 times 10 to the 18. So K is equal to 3.4 times 10 to the 18. That is the Kepler's constant for the solar system. Now, if dealing with any other body in the solar system, we can use this for the Kepler's constant, and we can use the radius of object that's in question and its period of revolution, or vice versa to calculate the other quantity. Now, for the moon around the Earth, you can do the exact same calculation. We'll just change some numbers. So the moon around the Earth will have the following radius and the following rotation in seconds. So same equation. So we get r cubed over t squared equals k. And we'll take the radius will be this. Period of revolution will be that. So throw it into a calculator. Just clear everything. So 3.84 to the 8. And we'll cube it. And we'll divide by 2.36 to the 6. And we'll square that. And altogether, we get, looks like 1.0 times 10 to the 3, 4, 5, 6, 7, 8, 9, 12. So 1.0 times 10 to the 13. So k would be 1.0 times 10 to the 3. So depending on the orbiting system that you're dealing with, the k value will change. Now this k value for the moon around the Earth will be constant for any orbiting body around. So constant for things orbiting around the Earth. There we go. A good example of this would be, say, if I wanted to put a satellite in orbit around the Earth. The satellite's radius and period of rotation would have to match this. So if I wanted to launch a satellite with a certain period of rotation, say maybe I wanted a 24-hour cycle as opposed to a 30-day cycle. If I wanted the satellite to orbit the Earth in 24 hours, I would change the period from, this is about 30 days, change this to 24 hours, convert to seconds, and then I could calculate what radius my satellite would have to be above the Earth to have a 24-hour period of revolution. Okay. Very handy for that kind of stuff. Okay. Or if I wanted to have a satellite orbiting at a specific altitude, then I can use this to figure out what is its period of revolution, so I kind of know how fast it's orbiting around the planet. Alright, so there you go. So there's Kepler's laws. Very brief look into it. It was a big part in figuring out a lot of planetary motions around our solar system, and then we were able to apply that for other solar systems. Right, your assignment for today then will be linked in the description below. Just a quick worksheet on putting some of the equations into practice. If you have any questions about that, then you guys know how to contact me.